Okay, today, sorry for my voice, first of all. I get to tell you all about quantum computing, and this is mind-bogglingly weird. I started learning about quantum computing about 4 months ago, and during this time I learned a lot of new stuff, and my mind was blown like 20, 30, 40 times. But I felt my brain growing. Turns out it wasn't my brain growing, I just had sinusitis. Some things I'm going to tell you today are not true. They are not true for probably 2 reasons. The first, we'll take shortcuts just to make it understandable. The second, I don't understand it. So let's be honest. I've spoken to PhD students, to professors about quantum computing, and each and every one of them says, if you meet someone who claims to be an expert that knows everything about quantum computing, they're lying, because the more you learn about quantum computing, the less you know. First, we'll look at classical computers. So, classical computers use normal bits, either ones or zeros. We know that. And what can we do with these ones and zeros? We flip them. That's all we do. Like your mobile phone, your MacBook, all it's doing, it's flipping bits. 1 and 1, 0. 1 and 0, well, we'll make it 1. That's all it's doing. Quantum computers are very different. They don't work like normal computers. They use something that's called a qubit. And some people think that a qubit can be 1, 0, and 1 and 0 at the same time. But that's not quite how it works. We'll get to that later. First, why do we need quantum computers? What does it solve? What does it do? If you look at the problems we currently have in IT, there are some problems which are P, polynomial. They can be solved efficiently on a normal computer. There are some other problems that are hard. That are problems that we currently don't know a smart solution of, or there just isn't a good way to make this happen on a normal computer. One of these things, for example, is prime factorization. So why is prime factorization important to us? Well, everything you do online depends on one thing. It depends on the fact that this is very easy. You take 2 prime numbers, multiply them together, and you get a large number. That's easy. Even your mobile phone can do that. Your pocket calculator can do that. This, on the other hand, is very hard. Given that number, what are the 2 prime numbers? This is the basis of RSA. This is the basis of internet security, everything you're doing online, your online banking. It's all based, most of it is based on this problem. That's a good thing. Currently, governments like the American government, they're storing all your information, even your secured information. Because maybe in 5 or 10 years, this isn't a hard problem anymore. At that point, they can read all your information. Think about that. If we have quantum computers, this will happen. A new group of problems will be solved when we have quantum computers. For example, prime factorization. If you look at the current best algorithm for prime factorization, which is the general number field sieve, you'll see that it quickly grows out of control into 1 billion years if numbers become larger. Shor's algorithm, on the other hand, which only works on a quantum computer, is linear. It has linear growth. So what is a quantum computer? How does it work? What is quantum mechanical phenomena? To do that, just like Malmberg, we have to do some basic physics. This is water. Water is made of molecules, H2O, yes. So 2 H's, 2 hydrogen, 1 oxygen. What if we want to break it up further? Well, then it's no longer water, then you end up with 2 atoms. The 2 hydrogen atoms and the oxygen atom. Atom, the name suggests, can't be split up any further. But it can. We know you can split it up further. For example, oxygen consists of 8 electrons, 8 protons, and 8 neurons. For some time, when I was in high school, this was the smallest you can get. Now we know you can get even much, much smaller. If you take, for example, one proton, you split it up into parts, you get 2 up quarks, 1 down quark. These are currently the smallest known particles, or are they particles, that we know. One thing I noticed, these names are very strange. There's even one called strange. One famous experiment is the double slit experiment. If you take a photon, a ray of light, for example, and you shine it through 2 small slots, this is what you expect to see. If you have 2 open doors, you'll see 2 beams of light. This isn't what's happening if you make it smaller. This is what will happen. It starts to behave like a wave. These photons interfere with each other, and you see a wave-like pattern appear. The weird thing is, that only happens if you don't know through which of the slots the photon went. If you measure through which slot the photon goes, this happens. Measurements will interfere, because if you do a measurement, that particle will suddenly no longer behave like a wave, it will behave like a particle. It's not just my headache, right? You're all having this. But these effects are really, really, really tiny. Can we see these effects? Well, it turns out you can actually see these effects. Who here has a Polaroid sunglasses? Or a camera with a polarizing filter? Cool. Sunlight, and all light that comes from a heat source, for example, a light bulb, is polarized in random directions. So it's either going like this, or like this, all directions. If you have a filter, just like your Polaroid sunglasses, it works like blinds. So they're like tiny slots, and if light is going like this, it will always hit the filter. No light comes through. If it's horizontal, it will just go through without any problems. There's no blockage there. If the light is going at an angle of 45 degrees, half of the light will make it through. The other half will be blocked. Sounds simple enough. Let's see that in action with a bit of Lego. It's a filter. So what happens when light passes through the filter? The thing is, if the light was at an angle, after going through the filter, it will be completely horizontally polarized. You will actually change the polarization of light. To see this more accurately, if we take another filter, we turn it 90 degrees, now all the light is going like this, no problem, goes through. All the light is going like this, 100% blocked. And this is actually what you can see next. If we turn the filter, no light will come through. We are actually changing light here. The most amazing thing is, what happens? So, first filter, it's randomly polarized, it goes through the filter, there's about 50% left. It's all horizontal now. If you have the second filter, no light will come through. It's black. So what happens if we add a filter in the middle, and we turn it 45 degrees, 45 degrees, I was correct. So now you get the following. Weird. By adding a filter in the middle, you're changing light, and suddenly light comes through again. This is just weird. I can't explain it, but it's true. I've got the filters with me. If you want to try this, if you don't believe my video, come to me and you can play with it. So this is actually what happens. After the first filter, 50% goes through. After the second filter, still 25% of the light goes through, but it's now oriented in a different direction. And after the third filter, still some light goes through, like we saw. Weird. So how do you actually build a quantum computer? Well, you could use photon polarization. There are quantum computers being built using these effects, and there's also the spin of an electron. Electrons spin around their axis. You can use the spin of an electron, or nuclear spin. There's also something called a Josephson junction. This is a very tiny electrical circuit that behaves like a quantum element. And there's also a quantum dot. Who here has a quantum dot television? No, you can actually buy these things. If you go to bol.com or Coolblue, or you can currently buy quantum dot televisions. It's the next thing after OLED. So if you want to buy a new television, watch for quantum dots. These are tiny particles that behave like quantum elements. You can buy these things. But you can also use these quantum dots in a quantum computer. So why don't we have quantum computers? Well, there are some tiny problems, because these effects, you need to manipulate these particles or waves. And if something is hot, and hot is like room temperature, they are all over the place. So in a quantum computer, you need to cool it down a lot to almost 0 degrees Kelvin. That's cool. So this is what a quantum computer looks like. I believe this one is made by IBM, and it has 5 qubits. So that isn't really shocking, but it looks like a very fancy chandelier, and that all has to do with cooling and the precision of the instruments. Bad problems. We're going to build a quantum computer here. To show myself that I really understood how quantum computers work, I went ahead and built a simulator. And it isn't that hard, actually. The physical side is hard, but the mathematical side, it isn't. But to really understand how a quantum computer works, we'll need my co-speaker, Mr. Cubitt. Is he here? Is he here? There he is. Come. He's coming. This way, please. There goes all the valuable time, no problem. Thank you. Oh. Say hello to Mr. Cubitt. If you want to understand how a qubit works, it's not just 1 or 0. The best way to represent it is using something called a block sphere, or a skippy ball. If a qubit is angled, this is his pointer. If the qubit is angled like this, it is a 0. If you measure this qubit, you will get 0. If you measure Mr. Cubitt like this, you will get a 1. If you measure Mr. Cubitt like this, who knows? It can be either. We'll get into that. So, mathematically, a qubit has a complex number that represents the chance of it being 0 and the chance of it being 1. So, yeah, just for reference, the total probability of one qubit is 1. So it's not that complicated. It's just 1s and 0s again. This is how we can make one in Java. I'm using Commons Math here, and as you can see, I've built a single qubit, and it has one complex number that represents the chance of it being 0, and one complex number that has the chance of it being 1. In this case, what will it be? 0, yes, because it has a 1.0 chance of being 0 and a 0 chance of it being 1. Einstein didn't believe in quantum theory, quantum mechanica. He thought it was just strange. And he said, God does not play dice with the universe. Turns out he was wrong, because if you want to measure this qubit, the first thing you need to do, call mat.random. Then we get a value. In this case, we've initialized our system to 0, so we will always get a 0. But in a later moment, we'll just pick a random number between 0 and 1, and we'll look at if it, according to the probabilities, becomes a 0 or a 1. So how do you manipulate these things? Well, normally, in a classical computer, you have gates. So you have AND gates, OR gates, NOT gates, which flip the bits. Turns out, it's very similar in a quantum computer. But we do matrix calculations. This is Pauly. Pauly is a bit of a prick, because he not only invented one gate, he invented 3 gates. And we can explain them using Mr. Cubitt. So the first thing he invented was, what if we turn Mr. Cubitt around this axis halfway? Okay, so we go from 1 to 0, back to 1 again. The poly X gate, it's just a NOT. It's the same thing, it's a NOT gate. If we turn Mr. Cubitt around this y-axis, the same thing happens. So they kind of both work the same way. They're both NOT gates, but you can see something different. Now you can see Mr. Cubitt's face. Now you can't. Now you can. If we turn it around this axis, you can still see his face. It doesn't disappear. It becomes even weirder if we turn it around this axis. So Mr. Cubitt is 0, Mr. Cubitt is still 100% 0, and Mr. Cubitt is still 100% 0. So you can encode information in a qubit that doesn't affect its outcome. We can actually use these kinds of things. So how would we make a poly X gate in code? Well, just like before, we still have the qubit, which is initialized as 0. But now we have this matrix, and it's 1, 0, 0, 1, 1, 0. And we can just apply it using Commons Met. We don't have to write any hard code. This is it. This is all you need to write a quantum computer simulator. One fun fact, all the gates are unitary, which means if you apply a gate and you do it again, you end up with the same thing you had before. This is true for all the quantum gates. So everything you do can be undone, except measuring. Because if you measure something and it jumps to a certain value, you can't undo that. Hadamard, he was a really smart dude. He was like, yeah, the X, Y, Z axis, why not use this axis? Now look what happens. Hey, what is it now? Is it 0? Is it 1? We don't know. It's 50-50. Exactly. And we can use that as well. It's just the same operation as before, but it's a little bit more complex matrix, but not a lot. And if we measure our qubit now, it doesn't always return 0. It returns 0 50% of the time, and 1 50% of the time. It's that easy to build a quantum computer. Using this, we can actually make Schrödinger's cat. Schrödinger, another famous physicist, he also didn't believe in quantum mechanics, and he thought the whole idea was crazy. So that's why he came up with a thought experiment to show everyone how crazy it was. If you put a cat with a little decaying particle and a glass of poison in a box, you close it off, you can't hear it, you can't see it. Within an hour, there's a 50-50 chance of the glass vial to break, and the cat will die. So what is the cat? Is it alive? Is it dead? Or is it both? Well, yeah, I don't know. But if we ask Mr. Cubitt, so what is it going to be? Let's measure it, and oh, it's a 1. The cat survived, yes. A controlled knot. There are actually more complicated things you can do with a quantum computer. Oh, wait, I've got to... This is how you program a quantum computer. The first line represents the first qubit. The second line represents the second qubit. The black dot is a control point. If this qubit is 1, this one will flip. If this is 0, nothing happens. It's a controlled knot. If you look at the matrix, it is twice as big because now we have 2 qubits. And this is the problem with quantum computers. Every time you add a single qubit, the whole probability of the system grows twice, grows twofold. So every time, if you have a 5-qubit system, it's 2 to the power 5. And if you have a 10-qubit system, it's 2 to the power 10. This quickly becomes rather large, and you'll be unable to simulate this on a normal computer. Also, right here, you can see the poly X gate, the knot, which is actually here. So it kind of, even mathematically, it makes total sense. If you combine the things we learned, you can do what's called a Bell state. First, we apply a Hadamard operation. So we do this. Now it's 50-50, 0 or 1. We don't know yet. And accordingly, we flip the other bit. What is the outcome? We don't know. If we measure, and we only measure in the end, if we measure a 1 here, this means this one will be 1, this one will be flipped, this one should be 1 as well. If this is 0, this was 0, this isn't flipped, so this is 0 as well. This is quantum entanglement. These 2 qubits are now entangled. If we would take these 2 qubits and we send them, we keep one at Earth and we send one to Mars, and then we measure them, you'll always get the same measurement on Earth and Mars. And you can actually do experiments to show that before measuring, these particles haven't made up their mind yet. There is no hidden variable. There is no, it was already 1 when we sent it, so no, it instantly changes the probability once you measure it. Weird. And sadly, the time is up. Normally, I would now go on to explain how Shor's algorithm works, how you can actually use this information to make a working quantum program. What you do is you put all the information into the system, then you take one measurement. But Roy, these measurements are random. What does it tell us? Turns out, if you do a measurement a couple of times, maybe 10 times or 20 times, you can get information from this. Very valuable information. Using these effects, you can do calculations like Shor's algorithm. You can actually take a large number and factor out the prime factors. For me, this whole experience was mind-blowing. For example, the thing with the polarizing filters, I can just keep playing with them. If you want to learn more about this, I'm actually doing a talk next week on DevOps. So if you're there, go to the talk. I can actually explain the second part, which is even more mind-blowing. But for now, I hope you learned something new. Thank you.